Hi guys, welcome back to my YouTube channel once more. Today we'll be dealing with strength of material. It is N5. We'll be dealing with bars. Actually, this topic is called compound bars, right? We'll be checking compound bars, stress and strain under compound bars, but we'll start by looking at bars placed in parallel. So yes, bars placed in parallel, which is module 3. Uh, Here we have given bar placed in parallel says here if a bar A and bar B in figure 3 point. Okay, let us forget because this one here I forgot to capture it well. So let us dwell in what is necessary. Actually, here what you're supposed to know: A and B are two bars are placed in parallel, right? So if bars are placed in parallel, they say the bars of, you see, both of them, they have their original length are equal. Also their extension, as you can see, they become equal. So we apply a tensile force there. So what we do here in this topic, we say because this bar A and bar B are made of different types of metal, that one. So we have to know that the total force, let's say the bar A and bar B will experience a different force because because of why we'll experience that is because they are made up of different types of material. So they have made of different types of material. Yes, they are bars, they have same length, but they are made up of different types of metal. So individually they won't have the same force that they will experience. So however, if we calculate the total force that is acting on this, we are focusing on our cross section. However, that total force, the force that will be applied there, the total force will be the sum, will be force that is applied on bar A. There on bar A will be the force there. Will add up the force. Will add up the force that bar A that will experience and bar B will experience. So will be the total force is B. The force that is the tensile force that is experienced by bar A and bar B, right? And also note, they say also the total, the change in, okay, the total, I can say extension is equal to the total extension of A, then the total extension of B. What I'm trying to say, they mean they are, you see them, you see the total extension is the same as the total extension of A and B, as you can check. That means the bar A and bar B will stretch, will be stretched at the same length, or I can say magnitude of length. If bar A stretches 3 meter, also bar B will stretches 2 meter. That means the change, obvious, the overall change you can take in, if you know the total change, the inland is the same, the extension there will be same as A and B. So we are hopeful you understand, but we'll understand this better if we indulge in some examples. So however, this is the extension, remember, but the extension we all know that is force multiplied by length over area over Young modulus of elasticity. So therefore, if we equate these two, for example, there will bring us here if we equate that two. But take a note, the length will be equal. We say the length are equal. They will even if they extend, they will still have equal length, equal extension. The length won't will be the same because they are placed in what? In parallel. So the length of A will be equal to the length of B when they are placed in parallel. So we'll simply cancel that length and that length. So the result of this formula there will have the result of SFA over area of A multiplied by EA, whereby this is equal to FB over AB multiplied by EP. So you see the length, because the length is the same. So okay, it's fine. Nevertheless, let us attack this example so that you'll understand this more better. So here ladies and gents, we have given example 3.1. Says readers for the rods. They say rods, that means there are two rods. It's not a single rod there. A and B of a length, the original length there, which is L, are placed in parallel. A tensile load of this, the force that they experience, act on the compound bar, is acting on all of this compound bar. You see, this is a compound when they are all packed there, when they are placed in parallel. But rod A is made of steel. Rod A is made of steel and has a cross-sectional area of that. We've given the area of the rod that is made up of what? Of the steel, while the rod B is made up of aluminum and has a cross-sectional area of that of 900 millimeter squared, right? Then they say calculate the stress in the two bars and their change in length. They've given Young modulus for elasticity of steel, which is that 210 gigapascal, of aluminum 75 gigapascal. So we should calculate what the stress. They want the stress in the two bars. They want the stress. So how can we attack this question? Here is the diagram that illustrates that this is their length. They're placed in parallel, as you can see. Then they experience a tensile. Their cross section of B. We have given this that areas there. Then yeah. So what do we know about this? Obviously, we don't. What do we know? We don't know the force that is acting on one. We only know the total force. This is the total force, the compound. But so far, what we know, what is important, what we know here, it's a formula. I've discussed about this. I said these lengths are equal. The change in length is equal. The change in length, the extension will always be equal, isn't it? So you can say the change in length, the extension at A will equal to the extension of what? Of the bar B. You understand? Even if the change in length will be equal as they experience the force, if the extension, if they extend, that will till that, because the experiencing force will be the same for both these bars. So okay, that we know. However, but we know that X is what? X is F. A, when I wrote A, you say it's the one of the steel, extension of a steel. This one of the aluminum. It's up to you. Maybe you can write maybe a little bit steel, aluminum, if we won't forget. Then we know that that formula will be force, but what? Steel. I'll just say steel for steel. This is multiplied by what? By the length. But the length of what? Of steel. Divide by the area of steel multiplied by the force, by the Young modulus of elasticity of steel must be equals to, remember we've given aluminum, force of aluminum multiplied by the length but of aluminum, isn't it? Divide by the area of aluminum multiplied by Young modulus of elasticity of aluminum, isn't it? But we know that we said the length is equal. They've given us, as you can see, this length, they have equal length, which is that is 300 millimeters. So far, since they're equal, we know maths, if you have equal sign, we can cancel this out and cancel that out. So you see what will happen. You can simply cancel that because will be equal, and this will cancel, will be left with formula that is like this. Now you understand. So yeah, so that is what we have there. So the force for steel, we don't know, we are not given. They did not tell us. We don't know the force of the steel over the area I've given, which is here is the area for the steel. For steel here is 400 millimeter. Then remember, you'll convert that, isn't it? Will be 400 times 10 to the minus what? 6. We convert because we've given in millimeter, times 10 to the power of minus 6. This is how we convert. Multiply by Young modulus of elasticity. We have given, which is the Young modulus of elasticity here, of that is 210. The other one is 75. So 210 times 10 to the power of 9, because it's in gigapascal. We have given that in gigapascal. So yeah, this will be equal, obviously will be equal. Now we don't know also the force of the aluminum over the area, that the area of the one is 900 millimeter, will be 900 multiplied by 10 to the minus 6. The area is there, which is okay. Yeah, that was the area. Then the modulus is 75, as you can see there, 75. Then gigapascal, this will be 75 times 10 to the power of 9. Right, so this is what we have there. Now it's a matter of maths, guys. This is a matter of maths. You can cancel what is it's up to you. Now it's a matter of maths, guys. There can make still the subject or A is up to you, but what I know, it's a matter of maths. Or if you can say F still, the F for force for steel will be equally multiplied there, right? But so far maths, I know what is in this side, this must cancel with that. What is the same, we cancel with that. You see, mathematical is correct, but okay, let me just do like this. Then if I multiply that to the other side, I'll have what? 4 times 10 to the minus 6, so minus 6 there, times 210 times 10 to the power of 9, when I multiply by F there of aluminum, divide by 900 times 10 to the minus 6, multiplied by 75 times 10 to the power of 9. Then this is the same, will cancel, that and that will cancel, as you can see. So you will be left with F steel equals to 400 multiplied by 210 over 900 multiplied by 75. Then all over this is what, there we have FA with the aluminum. Then you punch this on your calculator. Then as you punch that on your calculator, you'll get that F steel, get this ratio will be 1,244, because not a final answer, I'll make it to fourth decimal place multiplied by F force of the aluminium. So as you can see there, we have that we have this equation 1. We just leave it just a ratio. You can say okay, it's equation 1 or either way, it's up to you whether you write it equation or what, but this is what we have there. What do we know again? We've used the extension. What do we know again? We know that I've said again the total force. I've discussed about F total will be the force that experienced by steel plus the force that is experienced by aluminium. Right. So what will be the force of the, but steel here we know, as you can check there, of the steel is this one here. Remember, here is the steel. We substitute there at the space of the steel. We substitute there. If we can substitute, we know that will be 1,244,4, right? F aluminium plus F aluminium, but the total is the one for compound, is the one for the compound that is acting on the compound, is this one is acting on the compound on the both of this is 75 kilonewton. Then here we have 75 times 10 to the power of what? 6. So 75 times 10 to the power of 6 is equal, now these are like terms. Now this is like terms, you add these two is seamless, like 2,2. If you add your maths there, 24444 F L, like that. Sorry about that, guys. This is what we have. Then we divide both sides by 2,2444, right? That will cancel. Then if you punch this, you'll get this to be equal to what? Our FL will be equal to what then? 33,416. Then this is kilonewton. Therefore, you can write it up in a proper form there. This is what you have there. I just write that, I wrote that in kilonewton. It's up to you. If you can you can write it as a normal, let's say newtons. If you want, you can leave it in newton. So we have the one of the aluminium now. We have of the aluminium. But now we want of the steel. Of the steel we can get it because here, remember, from this equation we've made the steel here. If you may take a note, remember here, that is when we have that, you see, steel is that. So but now we know the steel, F for steel, we said it's equal to 1,444 multiplied by 1,4. That is what we have there. What I'm doing, sorry there. 1,4 F aluminium. So we can substitute F steel. We know that we'll simply just substitute 1,2444. Then substitute the aluminium is 33,416. I won't convict it. It will be in kilo. Remember, I just substituted this as it is in kilonewton. Take a note of your SI units. That means also the F of the steel will be in kilonewton. If you multiply, must be 41,584 kilonewton. So also this must be in kilonewton. Let me write my K accurate. So this is what you have now. We have this. Why we have calculated this is because they said they wanted stress for both. They say calculate the stress in the both bars and their change in length. So we know that the stress, nevertheless, the stress is equal to force over area. This formula does not change, is what we know. So, but now we have to indicate which one we are calculating for, because you have two bars there. It's up to you. Can say stress there. You can calculate the stress for steel. What will be force of the steel must correspond. You cannot use the force of something else, of the copper, but this must correspond. You cannot say you calculate the stress of the steel but use the force of copper, will be incorrect. This must be a correspondence there. Also, you are supposed to use the area of the steel. So yeah, then you know the rest is history. Just substitute. The force of the steel is that 41,584, but was in what? The force of the steel then is in it. It's in the one that is in kilonewton times 10 to the power of what, 6, or kilonewton times 10 power of 3, right? Divide by the area, which is the area we know it was 400 times 10 to the minus 6. Then if we punch this, they will get that the steel, punch that for if you punch this, you'll get that will be 103,96. Then it's in megapascal. Converted that to be in megapascal. That is your strength for steel. But remember, if we had two, what is the stress of what now? Of the aluminum will be the force of aluminum over the area of aluminum. So then what is the force of the aluminum? Is the one you have calculated here, right? The one that 33,416 kilonewton, 33,416 kilonewton times 10 to the power of 3, if I'm not mistaken. Yes, yeah, it's kilonewton. So divide this by its area, which was 900. I still remember, but it was 900 millimeter. Multiply by 10 to the minus of what, 6, because it was in millimeter, right? So then therefore the one of the stress of that of the aluminum will be 37,13 megapascal. We are done with this. They say what we should calculate again, and they are changing length, which is x. We're talking about the x. One, they are changing length. But it's nice if you can find. Remember, let me bring you back here. We said that total length, changing length, is equal to the changing length of the steel and all. That means if you can know one of these, because they are equal, if you can know the changing length of a steel is the same as we have known the changing length of all. If you can find one, the change, you know everything there, because all of them, they're equal. So you can find n. It's up to you which one you choose. You can pick, but we know that will be the same. let's say for argument's sake, if I can say steel, the change in length of the steel, then already, because now we have the stresses, if you have a stress, remember this is force, it's up to you. You can use this force multiply, there's this formula, it's up to you which one you use, multiply by length over area multiplied by Young modulus of elasticity. You can say of the steel is up to you, but since I've calculated the stress, I know this, I know what is that is equal to stress, but it's up to you which one you use. The formula is still the one and the same thing, guys. Still, that is same as like stress of the steel multiplied by length of the steel over area of the steel multiplied by Young modulus of the steel. Then now can substitute my thing. I know this, we've just calculated it. We got 190 like this times 10 power 6, but the length it was 300 millimeter. If I convert that in meter, it will be 0.3 multiplied by the area. We know that it was 400, then will be times 10 power 6, was 400 millimeters squared, and it is in it. So multiplied by Young modulus of the steel. Do not include the area, sorry. If there is a stress there, what I've did is incorrect. Yeah, will be like this. Remember, I've decided to use this one. Yeah, do not make that silly mistake like as I did there. Remember, I've decided to use this one. It has no area because the area is inside of that strand there, because I've decided to combine over Young modulus of elasticity, whereby of that was 200, isn't it? So this will simply equals to 200 times 10 was 200 times part is measured, we know it's becoming gigapascal like that. So yeah, therefore the change in length is still will be equals to punch this will be, what is that you'll get the you'll get a value like 0.0001485, right? This is what you'll get in meter, but if you want it in millimeter, multiply by 1000, then if you multiply this by 1000, you'll get this to become 0.1485 millimeter. But however, we know that the change in total for even their compound will equal to the change of the by A equals to the change of power at B. So from this formula we know that, but the change in length of the steel, the extension of the steel must be equal to the extension of that of the aluminum. So when we are already, we know whereby both they will simply equals to 0.1485 millimeter. So we are done with them, we got them. So this is how you drill these questions, guys. So thank you guys for your time. Please do not forget to subscribe to my YouTube channel and click the notification button so that you'll be notified whenever I post a new video. Feel free to comment and to like. You can like and share this to your fellow classmates. All the best. Thank you for watching.